You can review content from Crash Course Organic Chemistry with the Crash Course app, available now for Android and iOS devices.
Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry. We all smell bad from time to time, like after a workout, but imagine if your body odor smelled like fish all the time. This unpleasant sounding scenario is a reality for people with a rare genetic disorder known as trimethylamine. Their bodies can't produce the enzyme that oxidizes trimethylamine, so it builds up and is excreted through their sweat, urine, and breath. Trimethylamine is the compound that makes fish smell fishy, but it's actually used as a marker of freshness. It's produced from trimethylamine oxide by enzymes and bacteria. So the fishier a fish smells, the longer it's been out of the water. Amines are really important in biochemistry, medicine, and agriculture. And they're also involved in an ocean of important reactions. Let's dive in. Talking about amines can get a little complicated because there are two naming systems in use. To get common names, the alkyl group attached to the amine group is put before amine in the name, like methylamine, ethylamine, or propylamine. And of course, there's IUPAC, which we'll put on the screen. These are all examples of primary amines. Amines where one alkyl or aryl group is attached to the nitrogen in the amine group. Just like we have primary, secondary, and tertiary alcohols, we can have secondary and tertiary amines too. Unlike alcohols, where this refers to the carbon the hydroxyl group is attached to, a secondary amine has two alkyl or aryl groups directly attached to the nitrogen, and tertiary amines have three groups. Using the common naming system, we just list the substituent groups in alphabetical order. So a secondary amine with a methyl and an ethyl group attached to the nitrogen would be ethylmethylamine. And the fishy-smelling trimethylamine is a tertiary amine with three methyl groups attached to the nitrogen. The NH2 group is pretty low priority in IUPAC nomenclature, so we'll often see its prefix name, amino, when there are higher priority functional groups in a molecule, like 5-amino-2-pentanone and 4-aminobenzoic acid. Some molecules have more than one amine group. Diamines, for example, are used as monomers to prepare some polymers, like nylon from episode 31. They're also stinky. The aptly named cadaverine and putrescine are produced when bodies decompose, and they smell as awful as their names suggest. When it comes to shape, amine molecules have a trigonal pyramidal geometry. The nitrogen atom is sp3 hybridized, so the electron pairs around it take up a tetrahedral arrangement, like we see for carbon. Unlike carbon though, nitrogen has a lone pair of electrons taking up the fourth spot, giving the atoms the pyramidal shape. And in chemical reactions, amines are weak bases. The lone pair of electrons on the nitrogen can accept a proton, forming the conjugate acid, an ammonium ion. Looking at the pKa of the ammonium ion we generate tells us how basic the amine is. Remember, a low pKa means a compound is more acidic and more willing to give up a proton. So if an ammonium ion has a higher pKa, this means the original amine is more basic and more willing to accept a proton. If we want to increase the basicity of an amine, we can substitute in additional alkyl groups. Remember that alkyl groups are electron donating, so when an amine picks up a proton to become a positively charged ammonium ion, the alkyl groups help stabilize the positive charge. We can see this effect in action when we compare the pKa values of alkyl substituted ammonium ions to the simple ammonium ion. The basicity of amines can also be affected by resonance. For example, aniline, which is a precursor of the indigo dye used in blue jeans, is a much weaker base than alkylamines. This is because the nitrogen lone pair is tied up in the resonance in the ring. There are also nitrogen-containing heterocycles, which are cyclic molecules with nitrogen and at least one other element in the ring. When the cyclic compound isn't aromatic, these amines have basicities comparable to alkylamines. However, nitrogen-containing aromatic heterocycles are much weaker bases than alkylamines because of sp2 hybridization of the nitrogen atom. We saw how increasing S character increases the acidity of the hydrogen on a carbon. That's why we can deprotonate the hydrogen atom on a terminal alkyne. But in this episode, we're looking at amines, and protonated sp2 nitrogens lose their protons more easily than protonated sp3 nitrogens. So sp2 hybridization makes the conjugate base, the unprotonated amine, less basic. One of these heterocycles, pyridine, is a super useful molecule in the lab as a precursor. It's used to produce herbicides such as paraquat, as well as insecticides and antiseptics. If you need to use it though, you might want to hold your nose. Are you sensing a pattern here? Pyridine's aroma has been diplomatically described as very characteristic, and more bluntly is sour and putrid. So now that we really know what amines are and what they can do, let's talk about how we make them. There are a few ways we can do this, using a combination of nucleophilic substitution reactions and reductions. To make an amine, the simplest nucleophilic substitution is reacting ammonia with a haloalkane. The lone pair on the nitrogen grabs the alkyl group from the alkyl halide to make an ammonium ion. And by adding a base to remove the extra proton, we get a primary amine. But there's a little problem with this reaction. It just keeps going. Remember that more substituted amines are more basic than ammonia, which also makes them more nucleophilic. So the primary amine grabs the alkyl group from another molecule of the alkyl halide, forming a secondary amine, and so on. We end up with a quaternary ammonium ion, a positively charged nitrogen surrounded by 4 alkyl groups. Not great if we just wanted a primary amine. This overalkylation problem can be solved by converting the alkyl halide to an alkyl azide, another nucleophilic substitution reaction. We can then reduce the alkyl azide to produce an amine. But there's an issue with this reaction too. Azides, particularly ones with low molecular weights, can be explosive if they're not in solution. A third method is named the Gabriel synthesis after its discoverer. This uses the compound phthalimide to add nitrogen, and it's pretty cool because it adds a built-in amine protecting group at the same time. We actually saw this protecting group in our penicillin synthesis in episode 33. To remove that and get our primary amine, we can react the compound with hydrazine. A fourth option to get a plain old primary amine is reducing a nitrile. Like the azide reaction, the first step is nucleophilic substitution with the haloalkane. Then we can reduce the nitrile group to a primary amine. We also get a bonus carbon atom with this strategy. And lastly, in episode 32, we learned that we can make amines by reducing amides with lithium aluminum hydride. As a reminder, we can make the amides easily from acid chlorides or esters. Up until now, we've only made primary amines, but amide reduction also gives us a path to secondary and tertiary amines too. We just need to make an amide with alkyl groups substituting in for the hydrogen atoms. Reacting an ester with a primary or secondary amine allows us to do just that, and reduction gives us the secondary or tertiary amine we're after. There's also a reaction called reductive amination, which uses a milder reducing agent to add additional alkyl groups to an amine. Remember imines? They're molecules with a carbon-nitrogen double bond, made by reacting ammonia or a primary amine with an aldehyde or ketone. When making imines, nitrogen swaps out for the oxygen of an aldehyde or ketone, and we first get an aminium ion. In reductive amination, we then add a hydride to the electrophilic carbon of the aminium ion with a mild reducing agent. The alkyl group originally attached to the carbonyl group is now attached to the nitrogen. This is where we can customize what gets added to the amine, simply by changing the alkyl group attached to the carbonyl compound. While we're talking about aminium ions, we should highlight where they play a role in our mold medicine map of penicillin V. This step uses a similar reaction to close one of the rings. Like the reductive amination reaction we just saw, the lone pair on the nitrogen attacks the carbonyl carbon. A proton jumps to an acetate ion, which is grabbed by the negatively charged oxygen. Then we lose the hydroxide ion to form the aminium ion. So far, so good. Now, lots of different nucleophiles can add to aminium ions, not just hydride like we saw before. Here, the hydroxide ion we just kicked out can grab the hydrogen from the thiol group, and the sulfur attaches to the aminium ion carbon. And there you have it. We've closed the 5-membered ring in penicillin V. Filling in more of our mold medicine map is cool and all, but we have a couple more amine forming reactions to explore. I know I said that overalkylation can be a problem sometimes, but an overalkylated amine can be useful too. like quaternary ammonium salts are pretty good leaving groups. If we take a quaternary ammonium halide and heat it with silver oxide and water, a hydroxide ion plucks off a proton as the nitrogen leaves, giving us an alkene, water, and a tertiary amine. This is known as the Hoffman elimination, named after the chemist who discovered the reaction. Hoffman elimination is unusual because the major alkene it produces is the least stable alkene possible. Most other elimination reactions favor the more stable alkene. This quirk is because of the bulky tertiary amine leaving group. It sterically hinders the transition state for the more stable alkene, and therefore paves the way for the alkene that's less stable. And then there are enamines, which contain a carbon-carbon double bond next to an amine. Remember, they're an alkene plus an amine. Back in episode 29, we talked about forming enamines by reacting an aldehyde or ketone with the secondary amine, which, as we mentioned earlier, has two alkyl groups attached to the nitrogen. The first few parts of this reaction are identical to the imine-forming reaction that we've done a couple of times already in this episode. However, after water is eliminated, the secondary amine doesn't have an additional proton to lose to form an imine. So a proton is lost from the carbon adjacent to the one attached to the nitrogen instead. Now we have the enamine. Now, what we didn't talk about in episode 29 is what we do once we have an enamine. Turns out they act as nucleophiles in the same way as enolates and give us carbon-carbon bonds. So we can use them in the same kinds of reactions like alkylation. They have some advantages over enolates because we usually don't have to worry about overalkylation. Take a look at this mechanism. The nitrogen lone pair pushes down to help the double bond attack the halide in a nucleophilic substitution reaction. We get an aminium ion as an intermediate, which can't react more than once. So we can easily stop the reaction here. Not like the enolates we made in episode 43. We can use enamines for acylation reactions, which enolates do too. In both alkylation and acylation reactions with enamines, we reform an iminium ion through the course of the reaction, which we then hydrolyze in the final step to reform an aldehyde or ketone. All in all, a pretty handy set of reactions from some pretty bad smelling molecules. In this episode, we named different amines, explored amine basicity, use nucleophilic substitution and reduction to form amines, and use imines and enamines in carbon-carbon bond-forming reactions. In the next episode, we'll look at how we can use amines to produce diazonium salts and how these compounds are used. Until then, thanks for watching this episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.